In linear algebra, a squeeze mapping is a type of linear map that preserves Euclidean area of regions in the Cartesian plane, but is not a rotation or shear mapping. For a fixed positive real number a, the mapping is the squeeze mapping with parameter a. Since is a hyperbola, if u equals x and v equals y, a, then uv equals x, y, and the points of the image of the squeeze mapping are on the same hyperbola as is. For this reason it is natural to think of the squeeze mapping as a hyperbolic rotation, as did Emil Borel in 1914, by analogy with circular rotations which preserve circles, logarithm and hyperbolic angle. The squeeze mapping sets the stage for development of the concept of logarithms. The problem of finding the area bounded by a hyperbola is one of quadrature. The solution, found by Grégoire de Saint Vincent and Alphonse Antonio de Sarasar in 1647, required the natural logarithm function, a new concept. Some insight into logarithms comes through hyperbolic sectors that are permuted by squeeze mappings while preserving their area. The area of a hyperbolic sector is taken as a measure of a hyperbolic angle associated with the sector. The hyperbolic angle concept is quite independent of the ordinary circular angle, but shares a property of invariance with it. Whereas circular angle is invariant under rotation, hyperbolic angle is invariant under squeeze mapping. Both circular and hyperbolic angle generate invariant measures but with respect to different transformation groups. The hyperbolic functions, which take hyperbolic angle as argument, perform the role that circular functions play with the circular angle argument. Group theory. If R and S are positive real numbers, the composition of their squeeze mappings is the squeeze mapping of their product. Therefore the collection of squeeze mappings forms a one-parameter group isomorphic to the multiplicative group of positive real numbers. An additive view of this group arises from consideration of hyperbolic sectors and their hyperbolic angles. From the point of view of the classical groups, the group of squeeze mappings is SO plus the identity component of the indefinite orthogonal group of 2 times 2 real matrices preserving the quadratic form U2 minus V2. This is equivalent to preserving the form xy via the change of basis and corresponds geometrically to preserving hyperbole. The perspective of the group of squeeze mappings as hyperbolic rotation is analogous to interpreting the group SO preserving quadratic form x2 plus y2 as being circular rotations. Note that the SO plus notation corresponds to the fact that the reflections are not allowed, though they preserve the form. The additional plus in the hyperbolic case is necessary to specify the identity component because the group O has 4 connected components, while the group O has 2 components. SO has 2 components, while SO only has 1. The fact that the squeeze transforms preserve area and orientation corresponds to the inclusion of subgroups SO-SL, in this case SO-SL, of the subgroup of hyperbolic rotations in the special linear group of transforms preserving area and orientation. In the language of Mobius transforms, the squeeze transformations are the hyperbolic elements in the classification of elements. Applications. In studying linear algebra there are the purely abstract applications such as illustration of the singular value decomposition or in the important role of the squeeze mapping in the structure of 2 times 2 real matrices. These applications are somewhat bland compared to 2 physical and a philosophical application. Corner flow in fluid dynamics. One of the fundamental motions of an incompressible flow involves bifurcation of a flow running up against an immovable wall, representing the wall by the axis y equals 0 and taking the parameter r equals exp where t is time. Then the squeeze mapping with parameter r applied to an initial fluid state produces a flow with bifurcation left and right of the axis x equals 0. The same model gives fluid convergence when time is run backward. Indeed, the area of any hyperbolic sector is invariant under squeezing. For another approach to a flow with hyperbolic streamlines, see the article Potential Flow, section, Power Law with n equals 2. In 1989 Ottino described the linear isochoric two-dimensional flow as where k lies in the interval -1, 1. The streamlines follow the curve, so negative k corresponds to an ellipse and positive k to a hyperbola, with the rectangular case of the squeeze mapping corresponding to k equals 1. Stocker and Hosoi described their approach to corner flow as follows. We suggest an alternative formulation to account for the corner-like geometry, based on the use of hyperbolic coordinates, which allows substantial analytical progress towards determination of the flow in a plateau border and attached liquid threads. We consider a region of flow forming an angle of pi2 and delimited on the left and bottom by symmetry planes. Stocker and Hosoi then recall Moffat's consideration of flow in a corner between rigid boundaries, induced by an arbitrary disturbance at a large distance. According to Stocker and Hosoi, for a free fluid in S-square corner, Moffat's stream function indicates that hyperbolic coordinates are indeed the natural choice to describe these flows. Relativistic spacetime select for a here and now in a spacetime. Light radiant left and right through this central event tracks two lines in the spacetime, lines that can be used to give coordinates to events away from trajectories of lesser velocity track closer to the original timeline. Any such velocity can be viewed as a zero velocity under a squeeze mapping called a Lorentz boost. This insight follows from a study of split complex number multiplications and the diagonal basis, which corresponds to the pair of light lines. Formally, a squeeze preserves the hyperbolic metric expressed in the form xy, in a different coordinate system. This application in the theory of relativity was noted in 1912 by Wilson and Lewis, by Werner Grube, and by Louis Kaufmann. Furthermore, Wolfgang Rindler, in his popular textbook on relativity, used the squeeze mapping form of Lorentz transformations in his demonstration of their characteristic property. The term squeeze transformation was used in this context in an article connecting the Lorentz group with Jones' calculus in optics. Bridge to transcendentals. The area-preserving property of squeeze mapping has an application in setting the foundation of the transcendental function's natural logarithm and its inverse, the exponential function. Definition: sector is the hyperbolic sector obtained with central raised to n. Lemma: if BC equals AD, then there is a squeeze mapping that moves the sector to sector. Proof: take parameter r equals c, a so that equals takes 2 and 2. Theorem: if BC equals AD, then the quadrature of the hyperbola xy equals 1 against the asymptote has equal areas between a and b compared to between c and d. Proof: an argument adding and subtracting triangles of area 1/2, one triangle being, shows the hyperbolic sector area is equal to the area along the asymptote. The theorem then follows from the lemma theorem as area measured against the asymptote increases in arithmetic progression. The projections upon the asymptote increase in geometric sequence. Thus the areas form logarithms of the asymptote index. For instance, for a standard position angle which runs from 2, one may ask, when is the hyperbolic angle equal to 1? The answer is the transcendental number x equals e. A squeeze with r equals e moves the unit angle to 1 between and which subtends a sector also of area 1. The geometric progression e2, e3, n corresponds to the asymptotic index achieved with each sum of areas 1, 2, 3, n, which is a prototypical arithmetic progression a plus nd where a equals 0 and d equals 1.